Hello, this is continuing the series of videos on simple machines, this time looking at levers. So we've got three features that we need to think about with levers. We've got the effort, which is the force that we're applying to the lever. We've got the load, which is the force that we want the lever to apply at some object. And then we've got the pivot or the fulcrum, which is the point that the lever is moving about. This means we can have three different classes of lever, three different types, depending on which one of these is in the middle of the setup that we've got. So that'll become clearer if we look at class 1 levers. So in class 1 levers, we've got the pivot in the middle. So pivot in the middle, load is going up, effort is going down. So the key feature on this for analysing the levers is that the angles, if we draw in this horizontal line here, these angles are the same. So we've got either approximated similar triangles, or even if you think in terms of arcs of circle, the distance that these forces are moving through are proportional to their distance from the pivot point. Because you think arc length is r times theta. Well, we've got the same theta, we've got the same angle, so we can not think about the arc length, the distance that the forces, the load and the effort are moving through. We can just look at the distance from the pivot point, because these things are proportional to each other. So if we got a big D there for one of them and a little d there for the other one, our mechanical advantage is going to be the ratio of those distances. So the mechanical advantage is going to be our big D divided by the little d. Now we can see this is going to depend, the mechanical advantage, whether it's going to be greater or less than 1, is going to depend on where we put the pivot point. So in this case, I've put the pivot nearer to the load, so we're going to get a mechanical advantage greater than 1. Because we're moving our effort through a greater distance, so the effort must be smaller than the load, because it's moving through a greater distance than the load is. And this is all fitting in, if you remember, our standard principle of all of these simple machines is working is equal to work out for a machine that's 100% efficient. So we know that the distance that we're applying E through, so E times D, is going to be equal to L times little d. That's our work in, that's our work out. So that's what's going on with these. I mean, an example of a real world example of one of these class 1 levers would be a crowbar. So say you're trying to prise open the I don't know, dried on lid of a paint can. So we've got our can with the lid on it. You stick the crowbar in, so the load is at this end. That's what we're trying to lift up. We've got our pivot point here, very close to the load. We're flexing and pivoting our lever around the edge of the can, or the rim of the can, and then we've got our effort, which we're applying at the other end of the lever. So we're getting a large mechanical advantage here, because the load is so close to the pivot point. So that's our class 1 levers, which has got pivot in the middle. Class 2 levers, we're putting the we're putting the load in the middle for class 2. So this is your wheelbarrow approach. So we've got the pivot at one end, so that could be the wheel of the wheelbarrow. We've got our bar, we've got the load in the middle, and we've got our effort at the other end. So in this case, we're not changing the direction of the force in the way that we were with a class 1 lever. So class 1, we're changing magnitude and direction. Whereas for class 2, we're changing magnitude, that's for sure, but we're not changing the direction. And again, this is going to be, it's the same geometry really as a class 1 lever, because we got the same angle again, because the effort and the load, they're on the same bar coming out of the pivot. we're moving the effort through a greater distance compared to the load. So we've got the same way of calculating our mechanical advantage here in the ratio of the distances from the pivot point. This is another example actually of so we've got the wheelbarrow approach, but we've also got if you think of your calf muscle. So let's think of, you've got your foot. So say that's a bit of a wonky foot going up your leg here. So your calf muscle here attached to your heel with your Achilles tendon, you contract your calf muscle, which is applying your effort. You've got a pivot point, which is the ball of your foot, at the bottom of your toes. That's where you're going to be pivoting around, because you're going to be lifting your heel up. And you can lift your heel up a long way using your calf muscle, and that will lift up the whole of your body. And you can even do that standing on one leg. So we've got our load, which is the whole of your body, which is closer to the pivot point. So we're putting a smaller effort in. It's still a substantial effort. Your calf muscles are quite big, but we're putting in a smaller effort in your calf muscle to lift up the whole of the weight of your body. So that's another class 2 lever there, using your calf muscles to stand on tiptoes. Right, the third class we've got is the other effort in the middle. We haven't had effort in the middle. So this time, so what do we have? Pivot in the middle for class 1, load in the middle for class 2, effort in the middle for class 3. So this looks much like the class 2 lever. We've got our pivot point. We've now got effort in the middle. We've got load at the other end. This is your tweezers setup. Okay, we'd have 2 bars on tweezers, but you pinch the tweezers in the middle. In this case, this is great if you're lifting up heavy, light things. If you're picking up something light, but you want to move it a long way, then this is multiplying up the distance that you're moving things. So we've got a mechanical advantage here, which is less than 1, in contrast to for class 2, where we've got a mechanical advantage which is always greater than 1, because the effort is always further from the pivot point than the load. In class 3, the effort is always closer to the pivot point than the load. So we're always going to have a mechanical advantage less than 1. But that means we're moving things a lot further. Another example in the body would be your forearm and hand compared to your bicep. So if we've got elbow, so there's your upper arm, there's your elbow, there's your forearm. You've got your biceps are coming down and attaching pretty close to your elbow. So you've got your effort lifting up there, and that is then raising the load of your hand. So for a very small contraction of your biceps, you're going to get a large movement of your hand, because it's so much further away from the pivot point. This does have the disadvantage, of course, that you can't lift as much. You're going to be able to lift smaller weights using contracting your bicep and lifting a weight in your hand, compared to what we saw in class 2, where a contraction of our calf muscle can lift our entire body, because we're going from a mechanical advantage of greater than 1 for your calf muscle in class 2 to a mechanical advantage of less than 1 using your bicep in class 3. So that's the 3 setups of your levers, but they're all using the same geometry. They're all using this ratio of distances from the pivot point in order to work out mechanical advantage. We got various sources of inefficiency in these. Where are you going to get inefficiency in a lever? We were looking at inefficiencies in the inclined plane by looking at friction. Well, yeah, okay, we're going to have some friction kicking around in these. You've got the weight of the lever as well. That's another thing. So looking at this last one we had here, you've got the weight of the forearm. we might be wanting to lift something in our hand, but you've got to lift all the bones with it. So you're not getting our load, which is the object that we're picking up, isn't the entirety of what we're having to lift. We're having to lift the weight of the lever as well. We are going to have friction. You're going to have friction particularly at the fulcrum point, at the pivot point. You might also get flexing of the levers. With a crowbar, this is something that you might see, particularly if you're trying to prise open a jar or something using a knife or something. You'll see the knife starting to flex. So you're having to move the effort even further because it's bending round, and you're not getting as much output movement as you are if the lever had stayed rigid, because you're getting the lever bar is now flexing in that way. So that's going to be another source of inefficiency that we're going to get in levers. But that pretty much summarizes everything you've got on there. I mean, the maths is pretty straightforward when it comes to levers, but this is highlighting that we're using exactly the same methods of an analysis in looking at levers. One last thing I want to add on with this is, okay, it's great, this idea that you can get very large mechanical advantages, particularly we go back to that crowbar case. We've set up our pivot point really close to our load, which means we're getting a huge mechanical advantage. But what if we also want to lift something a long way? What if we wanted to lift up a car so we can change a tire or get underneath it, and we're wanting to use a lever to do that? What if we want a large mechanical advantage and a large distance? Well, we've got a problem here, because even if we move that lever all the way round to there, well, we're only moving up a tiny distance using this crowbar type approach. So you can get some more sophisticatedly engineered devices for this. So let's think of what we could do with this, with a couple of pins. So say you set up initially, you've got a pin which is our pivot point. We've got our load here, so we've got some huge mass that we're trying to lift up here. So say it is a car, there's the front wheel. We move our lever down a little bit, it lifts up the end of the car, so the car is now a little bit higher up. The lever's up here because we've moved it down. Right, okay, the car's moved up a bit, but we want to move it up a bit more. If you've got a second pin, you can then pin in location, so we can fix it. So we're still holding the car up, but we've got it fixed according to a second pin that then allows us, this is more or less switching it from class 1 to class 2. We've now put the pivot point at one end. The new pivot is now, when we lift the lever back up, it's pivoting around the end point, which is where we're holding the car. So the car's being held in place at what was the end of the load end of a class 1 lever. The load end of the class 1 lever then becomes the pivot point of a class 2 lever. Once we've raised the lever back up again, we can then drop a new pin in, as in we've raised now the pivot point of the original class 1 lever, and we can just repeat this over and over again. So we're going class 1 lever, lift up a bit, so we've moved up a certain distance, set that as the pivot of a class 2 lever, raise the lever up, set a new pivot point which is higher up for the class 1 lever, and then raise up again. So we're doing this alternating process where you're jacking the object up in the air by raising the pivot point. And that's allowing us to keep the large mechanical advantage, but also move through large distances by continually raising the pivot point up. So there are ways that we can make these levers more complicated, more sophisticated, in order to meet the needs of the load that we're having to lift. So I thought I'd just throw that one in there at the end. I mean, this is probably clearer if you load up a video or something like this on YouTube. I'll put a link in the the comments below this video, and it will make it clearer to see exactly what's going on here if that hasn't made sense, because it's quite hard to draw all of these things. But I think you'll get the basic idea that we're raising the pivot point up each time, and we're switching between class 1 and class 2 levers. So that's a summary of everything that's going on in levers, and that's the next one of our 6 simple machines covered.